This is tape 2 or class 2 on lecture number 7. Lecture number 7 was devoted to legacy LANs. If we go to the screen of the computer, your my WPI, we had so far like 4 parts. Was introduction, overview of the existing networks, overview of the technical aspects, and as of like one lecture before, we started to talk about standards related to local area networks. And in that area, our first lecture was IEEE 802.2 related to IEEE 802.2, which is logical link control. Then the next lecture that we started was lecture number 7, which was talking about Ethernet and other legacy LANs. So with that introduction, we can start this lecture, second part of lecture 7. What we did in the lecture 7 was we said that we would like to look into 802.3, 802.4, and 802.5. And these are the legacy, the first set of local area networks, standards that emerged in early 1980s. Among the 3, token bus is now closed and inactive. 802.5 and 802.3 are active, but 802.3 is the one which is dominant. So the way that our lecture series goes is that starting in the next lecture, we go 802.3 after legacy, which is fast Ethernet and other versions of Ethernet, like ISO Ethernet and Gigabit Ethernet. Detail of those things is in the next lecture. And there is one lecture above that, after that, which are other fast LANs, like 100 BGNE LAN, FDDI, and ATM LANs. And at that stage, we are finishing this part, which is part 4, which was about standards related to local area networks. Okay. Now, talking about this lecture number 7, last week, we started to talk about 802.3, and basically we went over the history, different options. But the main thing was this type of connections that they have, then physical layers that they have, in particular the physical layer for baseband, which is Manchester encoded. And then we came about talking about medium access control. So physical layer is very simple. Medium access control is also simple, has several parts that you would like to know. One part is the way that they handle carrier sensing. That was actually a main part of our lecture last time. And also the way that they carry the collision detection. So these are the analog part of the 802.3, and they happen to be like, especially in the early days, they were the weaknesses of 802.3. And then we talked about like the length of the slots and how does it relate to detection of a collision. So it takes about twice of the maximum transition propagation time to just find out that you have a collision in the worst case. So as a result, if you want to create time slots, you make it twice the maximum propagation delay. And we said that that is in 802.11, in 802.3 is equivalent to sending 512 bits. So each slot is 512 bits, which is also the minimum that you have to have. If your data is not large enough, then you have to add pads to make it 512, because if it is not 512 bits, then you may send a packet and assume that the packet was sent safe, but actually it had collided. Okay, you don't have enough time to detect the collision. Okay, so that's why you need to put that minimum length. The other reason, the other place that we use the minimum length was for the slots for retransmission. Okay, so then we came to talk about carrier sense multiple access collision detection, which is discussed earlier, but one thing which was new was this back-off algorithm. So we said that the 802.3 is one persistence carrier sense multiple access, okay, which means that listens to the channel so far as it's busy. As soon as it becomes free, sends the packet with probability of 1. So then inherently we have collisions. We need a back-off algorithm. And the back-off algorithm that we are using and we explained was the so-called exponential back-off algorithm. The problem with the exponential back-off algorithm is that it's first come, last serve. Okay. And then the good part of this is that it has embedded congestion control mechanism. Means that if you send a packet after a while and it doesn't go through, you can inform the terminal to stop or halt. So that was two important parts that will be used also later on when we talk about 802.11. Now, then the next issue was issue of the packet format of the packet itself. And the packet format is that it has a preamble, a starting delimiter, destination address, source address, and this is really data. But in order to identify the data, you need to have 3 fields because data cannot be, this field should have a minimum length. So what if you have no data? If you have no data, you have to put some pad. Okay, if I have no pad and data all the time, I have to have a length of field in here to say that how much data I have. Because otherwise I don't know which is pad, which is data. And then I have checksum. This checksum at the end is common with all the packets in the IEEE standards. The checksum is like using CRC code, cyclic redundant codes. Cyclic redundant codes, this is 32 bits cyclic redundant codes. What it does is that it takes the number of bits after here, after preamble, up to the pad, and divides that with a number which is 33 bits, and it's a prime number, and finds the remainder of that number, remainder of that division, which is 32 bits, and that 32 bit is this checksum, the checksum that we have in here. Okay, this type of code is called what? CRC code, and it's used also in 802.5 and 802.4. Okay. Now this was something that we didn't cover last time about how this coding works. Now the other interesting point that I told you that in here again this is a weakness of 802.3. You don't have this format in 802.5 or 802.4. But later on when 802.3 became dominant, actually this became a strength. Because when you have length of the field in here, this 2 byte can represent numbers which are much bigger than 1500, which is the length of the data. So as a result, you can put lengths in here which are not real lengths. And then the destination address or any terminal can read that address. If the address is not correct, they can associate it to something else. What is that something else? Is like control signals. 802.3 originally was only one packet. That was the good part. Okay, one of the reasons perhaps for the success. Okay, but on the other hand, as time passes by, you feel that you need some sort of control signaling. How do you want to embed that? You put it in here with an address which is more than 1500. Examples of that is like virtual LAN and full duplex operation that we will study in the next lecture. Okay, so these are the things that you want to remember about the packet length. Another issue in this packet format, I mean, I would like to mention is this issue of preamble. Okay, if you have like in here in 802.3, you have like analog circuits up front. Okay, and for the detection, etc. Now synchronization needs some preamble, extra bits to synchronize with that packet. If you go to digital format, for example, 802.5, you don't need it. Okay. Then again, you go to FTDI, which is a little bit shakier channel. Again, you need it to just minimize the jitter, actually, in there. Okay. So this preamble field sometimes is there, sometimes is not there. Anytime that you have, like, modulation techniques, definitely you have preamble. I mean, means that if you have broadband, always you have preamble. But if you have, like, baseband, in 802.5 you don't have it. In 802.3 you have it. Okay. So that's like format of the packet. But each of these packets that you're sending in local area network has the source and destination address. That's the most important thing. Okay. The rest is just supporting material. Then we went over like configurations, and this is the place that we left in the last lecture. Okay. Now, so Ethernet was like basically a medium in which you send your packet in the air and destination address picks it up. Okay, this is the idea when it came to market. Okay, but later on when they went to the star, etc., it's still the same concept is in there. But you can restrict this availability or you can leave it for everybody. This is the basic concept of Ethernet. Okay, it's a medium just like propagation medium, like radio. You put everything, everybody hears that. Whoever who wants tunes to you. Okay. Now, 802.5, which was from day one supported by IBM, uses token ring, and it is a little bit different. Okay. Now, the first thing is that just about the token ring. Token ring started around the same time that Ethernet started. Ethernet was in the other three companies, which were Xerox, DEC, and Intel, and this was IBM solution. Okay. Then, similar to 802.3, this 802.5 was also intending for commercial and light wave industry, office environment. Okay. Now, in here, there is a difference between 802.5 and Ethernet. 802.5 really is a collection of point-to-point connections. Okay. It's not like Ethernet that you drop everything in and everybody listens to that. In here, you have a bunch of point-to-point connected one after another. Okay. If you have a situation like that, it is efficient and fair under heavy load. If you have too much load, it's good. But if you have light load, Ethernet is better. Okay, because Ethernet doesn't have any overhead. In order to create these, connect this sequence of point-to-points to one another, you need to maintain a ring. And to maintain that ring, you have overheads, extra overhead. These overheads are the packets that you have to send to maintain this ring for operation. Okay, so it's more complex, but that complexity is not that much really, but it still is more complex. Okay, but what you get is you have more efficient. Now, 802.5 originally was defined for shielded twisted pair and unshielded twisted pair, similar to legacy 802.3. Okay, but this one was a token ring, this was a ring operation, the other one was what? The bus operation. So it's ring versus bus. Now, as I mentioned earlier, this is a fully digital network. There is no carrier sensing in there, analog parts. You can implement it using all digital circuitry. Okay, that's then the advantage of this. So this is 802.5 overview. Now, what is the implementation of that and what are the differences? Let's look at the physical layer. Physical layer of 802.3 was what? Differential Manchester coding. This is also differential Manchester coding. The only difference in here is that you have two symbols, high, high, and low, low. You remember that in differential Manchester coding, Manchester coding in general, you have a high, low for every bit. Okay? In here, you have some bits which are high or low. And you can use them for signaling. For example, for the start of delimiter, for the end of the delimiter. Okay, to start and end of the packet, you can put things which are not Manchester coded. They are high or low. That's one of the differences. Okay, but other than that, physically it looks very similar. Then they have basically 3 successful standards in there. One standard is at 4 and 16 for shielded twisted pair. 2 options, 4 and 16. The other one for unshielded twisted pair at 4. Okay, so for 4 megabit per second, you have 2 shielded and unshielded, 16 shielded twisted pair. Okay, and then in addition to that, when they went to the fast Ethernet, these guys also went to the fast token ring, if you want to call. Fast token ring is 100 megabit per second. Okay, but the way that the physical layer that they are using is the same as physical layer of fast Ethernet. That we talk about it later. Okay, so physical layer is the similar pattern happened also into what? 802.11 and HyperLAN activities. 802.11 and HyperLAN 1 were competitors. Then HyperLAN 1 was not successful, so for HyperLAN number 2, people came to 802.11a community and picked up that physical layer for HyperLAN 2. Okay, the same thing has happened into this community. Okay, so 802.3 was more successful. Then 802.5 people, they merged with them really to go for fast Ethernet, which is 100 megabit per second. But they adopted the physical layer. They went to design their own MAC layer, which is different. As a result, but since 802 communities are separated with the MAC layers, these guys, they had to devise a new MAC, so they had a new actually thing. They had a new community. Okay, so they are not either 802.3 or 802.5. Okay, and that's what we call it 100 base any LAN. That we discuss it later on. Okay, but anyways, the data rates are 4 and 16 and 100 megabit per second. For legacy 802.5, it's 4 and 16 megabit per second. Okay, physical layers. Okay, all digital. Now, MAC protocols. MAC protocol for this, so physical layer is the same as the other one. The only thing is that I have high and low. Okay, and my data rates are different. If you notice, the data rates 4 megabit per second is less than 10 megabit per second for the environment that we talked about, for the shielded twisted pair and unshielded twisted pair. In the 802.3, you can provide 10 megabit per second there. Anyways, now how about the MAC layer? MAC layer of 802.3 was carrier sense multiple access with collision detection and with exponential backoff algorithm. Now, how about the MAC of 802.5? MAC of 802.5 is a ring, is a token ring, means that I have a token inside there that anyone who wants to transmit the information picks up the token from the ring and sends the packet and then puts the ring, puts the token back. One good example that Starlink has is this one. At the beginning, this token is circulating inside the ring, and I have like 4 of these terminals. Terminal A wants to send the packet to terminal C. It picks up the token, puts his packet inside. Packet comes in here and passes through D, and then comes and passes through C. When it wants to pass through the C, it's get acquired by C. And then, but it continues the travel. Always you have 1 bit delay at each terminal. Okay, at that 1 bit, you read that bit, you can send it in, okay, you can send it out, you can send it in and out, or you can just send it out. Okay, so they send it out in here, okay, and also they collect it because the address is the address of the C. Okay, now C has received the data, but still the packet is in the air. Packet comes, when it comes back to A collects it without sending it back. When it collects it, starts to send the token back into the air. Okay, so each terminal who produces a packet also collects that packet. And after collected the packet, puts the token inside the ring. This way you have a sort of automatic acknowledgement check. Now, this is like token comes inside here. The example still continues. Now this time terminal C wants to send. Terminal D doesn't have anything in the buffer. Terminal C wants to send something. Terminal C picks up this packet, which is the token, and it has two packets in the queue. One to go to A, one to go to D. Puts those two packets inside. They come. A goes to A, then D goes to D, and both packets are coming back to C. C collects them and puts the token back into the air. Okay, so this is the basic mechanism of what? Token ring for the Mac. Now, there are a couple of now interesting things in here. Number one is that when this destination is picking up the packet, okay, there are 2 bits inside the packet that it will change. Actually, that's at the end of the packet. Okay, they change those 2 bits just to provide some signaling with the source. Okay, those 2 bits are called AC bits. Okay, one of them is turned back as soon as you read it. I mean, has passed through your terminal. The other one is if you accept it. Okay, so you have 2 conditions in there. One is that the data comes to you, passes through you. You signal that with first bit that yes, this signal passed. Number 2 is that when it's passing, if your buffer is not full, you will accept it. Then you turn another bit. So you may be alive, but don't accept it because you are congested. You may not be alive, then you don't do anything. So with 2 bits, you are signaling to the source that whether you read the packet or, and also whether you were available at all. Okay, so those 2 packets, the AC packets, bits, we will show them later on. That's at the end of the packet. They fit these 2 bits. Okay, now A and C bits. If A and C, when the packet arrives back to the source, if it is 00, means that destination is out, is not working. If it is 10, means destination was on, but did not accept the packet. If it was 11, means you are all set. There's a sort of acknowledgement plus checking of the network. One of the things which are important in the ring operation is that you have to always check the maintenance and operation of the ring. But in Ethernet, you don't need that. Okay. Anyways, as we talked earlier, original ring was like a real ring, but real ring has problems for physical maintenance. Means that if one of the rooms is broken, then you have to go to every room to find out who is there. So as a result, as we talked earlier in previous lectures in topology, they do it in practice like this. Means that for each room, they take 2 wires. One goes in, one comes out. Okay, but everything comes to a central wire center. This is just for physical maintenance, not for the maintenance of the loop. Just for physical maintenance. Okay, so this is how they use it. And it's not a problem, especially with twisted pair, because always twisted pairs are available in bundles of more than 1 pair. So you use 2 pairs rather than 1 pair. Okay. Now, issues of ring maintenance. Ring maintenance and issues related to that. That's a very important issue. One issue is that if you have a ring, you have to maintain it. Why you have to maintain it? Because you need somebody to take care of duplicate tokens, for example, if token is duplicated. Also, you have to take care of initiation when you start everything. Okay. And also if a terminal goes out. Okay. So there are a bunch of operations that you have to do. Now, there are two philosophies in there. One is that you take a terminal, and this terminal will be the manager of the network. Okay. This is the one that they do in 802.5. So you have like distributed, you have centralized algorithm really to maintain the network. Okay. The other philosophy is that you will have a distributed maintenance. That's the one that is used in 802.4. In 802.4, this is designed for what? Manufacturing environment. In manufacturing environment, they want to have more and more reliability. To have more reliability, you cannot rely on a central station. In here, this is for office environment. Reliability is less important, so you can rely on a central station. That's the difference between the philosophies. Okay. Now, what you have in here, unlike 802.4, in token ring, you have a monitor station. What does this monitor do? Monitor station. What does it do? What is its responsibilities? One is handle the token loss. The other one is clean the garbage. Any frame which is garbled around. Means that you have a frame that some error has happened in the address and there is no destination for that. So it's just circulating in the ring. Somebody should take it away from the ring. Detect orphan packet. Actually, orphan packet is like that, using monitor bits in the AC. Okay, and they keep length of the ring longer than the token itself. Okay, this is like responsibilities of the monitor. Then they start with certain signaling, and then they do the addition and deletion. Everything is done at the what? At the central monitoring station. There is no need to go over like detail of these things. I go over just the top layer, how they implement it. The first thing that they do is that they have to define like MAC frames. Now, the MAC frames in here are going to be a little bit different. In these MAC frames, I have to have provisions for sending control packets. What are the control? For example, token. In addition to token, I have a bunch of other packets that I have to use for maintenance of the ring. Okay. So they come up with this packet format. This is the packet format. They have a start of the delimiter, which is very similar to what you had in the 802.3. But in 802.3, you had a preamble. In here, you don't have that preamble because it's a digital network. Okay. Then they have AC. AC is access control. Okay. Access control is in here. Is the one which provides you with the priority bits. Because in 802.5 and 802.4, both of them, one of the advantages is that you have priority. Okay. Now, however, as I mentioned earlier, this priority has certain problems. These priorities, they don't pass through the bridges. So it's only for local area network. As a result, if you want to use this priority scheme for providing quality of service over the entire network, they are not useful. So though these were, how they did it originally they did it in 1980s. At that time, nobody was caring about quality of service because voice and data is completely separated. When voice and data started to emerge in mid-1990s, they started to think about quality of service. But at that time, there was no quality of service. Why they wanted priority, as I mentioned in some of the previous lectures, that was for, like, you go to a college, you want to give more priority to professors than the students. You want to give more priority to network manager. As a result, they were provisioning these things. Okay. But anyways, this is for that priority. And then they have frame control. Frame control is the one that is used to implement instructions, really. Okay? You have to have a bunch of instruction sets to communicate between the terminal. Those instructions are coded in frame control. Frame control has two start of the frame bits, which are frame type, and then they have these things which are control bits, which you can change them and you come up with different things. These two bits could be like for control, signaling, whatever. You can just code them in that sense. And then these are the minor instructions under those type of thing. Okay, so that's it. And then after that, they have destination address, source address, exactly the same as what? The same as 802.3 with the same length, 6 byte. Okay, and then they have the data. In here, the data is not divided in 3 parts. The data is only one part. There is no length of the data, and there is no path. Okay. After the data, you have your error correcting code. Error correcting code in here is exactly the same as error correcting code that you had for 802.3, which means that it's CRC codes with 32 bits remainder. Okay. So a prime number with 33 bits is used. Now, what is the number? The number you get from the start of the delimiter all the way up to here. You divide it with that prime number, which is 33 bits, and the 32 bits which are left over, you send it in here. Then you have end of delimiter, which is the end of your packet, and at the end you have FS, this frame status. This FS is the one which carries A and C bits. Okay. What it does, it carries AC, then there are 2 bits reserved for future, again AC, and 2 bits reserved for future. So actually they are sending the AC bits 2 times in this packet. The reason is that this packet does not have any protection, any coding. Okay? While the rest of the material, they have coding. In addition to that, you have 1 byte, and you can fit it in. Okay? So they have put 4 bits for 2 times sending AC bits, which are important bits, and then 2 reserved for the future. 2 bits reserved for the future. How about end of delimiter? End of delimiter is like, consists of a bunch of J and Ks. What are these J, Ks? These are those symbols which are not differential Manchester coded. High, high, low, lows. And for different options, they may be different. Okay, for baseband, they are high, high, low, low. Okay? And then, because these are different from the actual thing, you can realize that when this packet has been finished. More or less, this is overview of this thing. Okay, overview of all the packets as much as it needed. So the difference of this packet format with the 802.3 packet format is that you don't have preamble because it's digital. You have control field, which allows you to generate what packets that you don't want, packets that you want for control and signaling, and it has this AC bits at the end. In addition to all of that, you have symbols which are not Manchester coded, low lows and high highs. More or less, that's what it is. The last thing which is in here is the length of the packets. Length of the packet, if you remember, length of the packet in 802.3 was how much? 1500 byte. In here, for 4 megabit per second, you have 4550 byte. And if you go 16 megabit per second, it's 18,000. So it's like actually an order of magnitude, more than 10 megabit per second. Why you can do that? Because this one doesn't have the analog circuitry. Okay? And it's digital service, point to point. Okay? So these are like advantages that this guy. Now, if you have now longer, why they want to have longer packets? Because they can restrict, they can make the length of the transmission higher, okay, in order to have shorter length packets. The reason is that they have overhead in here, additional overhead for maintenance. Okay, they want to keep those overhead at a reasonable thing, which is comparable, let's say, with 802.3, at a negligible level. Okay, so they come with this compromise. Now, yes.
Error checking in here.
Yes.
In the CSP, and we have one delay at each filter in the ring.
Yes.
Now, when does the FCS actually come into play? Because we start transmitting the signal.
No, when you pick up the whole packet. See, packets bit by bit passes through you. Okay. When it passes through you, and it's yours, you take all those bits yourself. So you have the entire packet. When you have the entire packet, then you look at FC.
It's and put it back onto the ring, so the packet would reach back the original source and tell him that the packet has reached.
A and C was only because that if you have received this thing or not.
Okay.
If you have received it, number one, to number two, your buffer was full or not.
Okay.
Had nothing to do with FCS.
Okay. So the acknowledgement is only to the part that whether we have received it or not, and not to the part whether we have received
number one, whether your terminal was alive or not. Number two, whether its buffer was full or not. Okay, it has nothing to do with FCS. Now,
Another question?
okay, yeah, but and also there at the end of the packets, you can't change it in a sense because it's at the end of the packet. Yes.
In the bottom, the first bullet says that the high and low are in the SD and FS.
Yes.
Is it in the FS or is it in the ending delimiter?
That's in the ending delimiter, actually. It should be ending delimiter. Yeah.
Okay.
That's right. This is in start of delimiter and end of delimiter. I have to change that. That's an error. Okay. Oops. So now this is the MAC frame. Now with that MAC frame, now you can design a bunch of like instructions. These are instructions that they do in there: duplicate address test, beacon, claim token, purge, active monitor preset, a standby monitor preset. And using these instructions, they try to implement variety of operations which are used for maintenance of the ring. Okay. For the maintenance of the ring, I will have a bunch of instructions. Okay. Those instructions are not only one instruction. They may be sequence of instructions. So I need like a programming language to write in that programming language my protocol. Okay, to maintain it. So these are the instructions in that programming language that they use in order to maintain the ring. Okay. Now, but let's go to the issue of priority. I mean, for maintaining the ring and handling the priority. The first issue is that how they handle the priority in the 802.5. This example is coming from Stalling. It's a very good example which describes the general format of 802.5's priority scheme. Okay. The priority scheme is like this. A is sending a signal, sending to like B, and the signal, the packet. The packet is coming through. Okay. Packet, when it comes in here, B is picking up the information and comes back to A, and A wants to pick it up under normal condition. Now, in this particular example, what he assumes is that when A is sending to B, D has a packet which has higher priority than this packet. Okay. When this packet is passing by, we had a field for priority, so it had a certain priority in it. D reads that priority. Priority of the packet that D wants to send is more than that packet. So what it does is, when this packet is passing by, changes the bit for priority to the higher priority. When it comes back to A realizes that priority has changed. So realizes that there is somebody in there in the network who wants to send the next packet with higher priority. So A knows that. Since A knows that, as soon as he collected this packet and wants to send its own packet, sends its own packet, after it collected that packet, sends the token back to the network, changes the priority bit of the token to the priority which was demanded by D. So now this packet, this token which comes to the ring, has a priority which is set at the level that D wanted. Okay. At the same time, A will record the previous priority that it had. Okay. Now, this token comes in, and let's say B wanted to send something. B reads this packet, tokens, priority, and sees that priority of that is higher than this guy. So let the token go. Token goes, and then D picks up that token. When it picks it up, then it sends its own packet. The packet goes through, comes back, and D collects that packet. When it collected that, it has to release the token. When it releases the token, still it releases it with the new priority. Okay, with the priority that it had. Okay, that one comes in here. A picks up that packet because it knows that it had put this token into the network, sets it with the previous priority, and then puts it back to the network. And operation starts to continue. Okay? If D wanted to change that, D didn't know that what was the previous one. Okay? So actually A has to pick it up to change it to the previous priority. So the normal operation comes back. Very, very elegant. These type of algorithms today are in a sense interesting for operations like Bluetooth, ad hoc networks, and things like that. Okay, but not exactly the same algorithm. Similar algorithm, a little bit modified. So for that purpose, it's not bad to know that what other people have used. But it doesn't have much of practicality today because 802.5 is going out of it. So how do they implement this thing now? They have this environment and they want to implement it. In order to implement always the same as in Bluetooth, the same in here, you need a bunch of registers. You need a bunch of registers to implement the algorithm. How does these registers communicate with one another? Through those control signaling, control packets. So I have a bunch of registers which keep the track of the neighbors, for example. In Bluetooth, that's the neighbor. In here, for other purposes. They keep the track of where is the token, what are the priorities, etc. Based on those instructions, they implement the algorithms. Okay? So where are those instructions? They are part of the packet, the long packet which contain the source, destination, and the data address. Okay? This is like token holding action for that's the implementation of that. I think you can go over that yourself. Now, how do they put together a ring which is bigger? As we continued in 80s and we came to early 90s and switches came, like switched LAN came to the market, switched LAN also came to the token ring as well. Now, how does a switch work in the token ring? This is one example that Stalin has, which shows how a switch hierarchy works in a token ring operation. Okay, so I have these terminals, these two terminals connected to this switch, and then there is another switch under that. There is another switch in here at the same level. They are connected to one another. Another switch under this switch. Now, if it was like 802.3, it was very easy to see how they work, because there was no token passing involved between everybody. It was just like telephone network. In here you have a token which is passing through all of these terminals. How do they pass those tokens really? Okay, so the order is like this. It starts from here. This guy has the first hit, Then this guy has the second hit. Then comes to this port. When it is in this port, comes to this switch. Then this guy, and then this guy, and then comes back and goes to this port. Then comes to this port. From this port, it comes to this switch, comes to this guy, then comes back and goes to this terminal, and then it comes back all the way to the original. Okay, so that's a sort of like token around all of them. Okay, now summary, comparative summary of 802.3 and 802.5. The first issue is issue of popularity. That's the most important thing. 802.3 became popular. 802.5 lost its popularities. As I said, maybe a couple of 802.5 up to like 1998% of the market. But strictly on the IBM-based organizations. Okay. Now, which still they were doing the financing systems. Okay. Now, but what happened? What was the reason that 802.5 won? 802.3 became popular. This type of questions are just like questions that how come Microsoft won over Apple? How come VHS won over Beta? Okay. In telecommunication industry, always you have questions like that. And as they say, never best technology wins. Okay. It's the best marketing which wins. Okay. Most of the time. At least when they are very similar. At the time, VHS, certainly it was the case. Okay. And could be the case between 802.3 and 802.5 too. Okay. And then is openness to the market. Openness to the market that Microsoft had. The same way, I think, 802.3 was better marketed in a more open environment, possibly. But who knows? But the fact is that the reality of the popularity is not directly correlated to the technology. But anyways, now forgetting about that, let's look at the comparison of the technologies. How does 802.5 technology compares with 802.3 technology? Okay. In terms of simplicity of the protocols, it's very difficult to say, but 802.3 is very simple, but it is analog. It has analog parts in it. It's not as clean. Okay. Complexity of the algorithm, 802.3 doesn't have any algorithm. There is no algorithm associated with 802.3. It just take the packet and put it in the network. In here you have a bunch of algorithms. In a sense, that algorithms could give you assurance that this is a better network, more controlled environment, and leaves more options for improvement. Performance in terms of delay in low loads. If the load is low, 802.3 doesn't have much of delay. The same is with the throughput. So throughput is very high. Delay and throughput really are very similar. They're the same in a sense. Okay. So when you have low load, 802.3 has not much of delay, and throughput is very good because you don't have any overhead. When you go to high load, then 802.3 is going to have a lot of collisions and a lot of retransmissions, which causes a lot of delay. Okay, but 802.5 doesn't suffer from that, since it's a regulated environment. So the classic thing of 802.3 versus 802.5 is that for low load, 802.3 is better. For high load, 802.5 is better. And I think I mentioned that before, and we will show that like numerically, quantitatively, when we talk about performance analysis. We have one lecture on the performance. The next issue is quality assurance and priority for voice and video operation. This discussion, I mentioned it earlier, quality assurance is more guaranteed in the 802.5, but the problem is that that cannot go beyond the local area network. I mean, if you have bridges, you cannot carry these priorities after that. So that one is not helpful, in a sense. And as we said, yeah, no need for modems or analog circuitry for 802.5. So that's the story of 802.5. And at the level that we wanted. Now, 802.5 also is very similar to FTDI. FTDI was more successful in a sense that it captured the 100 megabit per second market for a while and was dominant. Okay. And we discussed that 2 lectures after, in lecture when we talk about other fast LANs. Yes?
We had this quality of service thing, and you showed a diagram which had the switches there, and the token used to pass through that. Now the priority is actually implemented as a part in the token in the packet itself. So the token also.
It's inside the protocol, inside the token. Yes, yes.
Now that thing is actually going through those bridges. So how come is it not feasible to?
No, when you want to go out of that network, you want to go to the internet, etc.
Okay, so
bridges which I mean, yeah.
Okay.
Yeah, bridges which are, those are switches really, the ones that are here. Bridges that when you change the protocols, when you connect it to another one, you wipe out. You go to 802.3 in between, you wipe out all those priorities and doesn't come back. That's more or less what it is. Okay. Now, 802.4, token bus. This token bus actually, if you go to the recent 2003 book by Tannenbaum, he doesn't even mention 802.5 much. Okay. In the year 2000, our textbook, he has 802.5, doesn't have 802.4. But in the previous version of, previous version of Stalin, he had 802.4. Again, I had some results from there, some of the overheads. I thought I will put it in here. Why? Because it's good to have them around, just to see that how things evolve. But we go over them very quickly. We have like another 10-15 minutes on that. Now, 802.4, the first thing which came at the beginning was that, why do you want another standard? Obviously, 802.4 people, as we said earlier, they were interested in factory environment. And in the factory environment, people were suspicious about 802.3. Remember, 802.11 also started in the factory environment. People were thinking at the beginning, they had this perception that factory is something completely different. But that perception today does not exist in that sense. Okay. But what was the perception of the people about the factory? What is different about the factory? They were assuming that they are talking about machines of the future at that time. They are delay sensitive. Okay. Since they are delay sensitive, because you are controlling this machinery in the factory environment, and you have local area network to control that, then 802.3 cannot do that because it has no control over the delay. That's what they were arguing. Number two is that if I have a machine which is more important than other machines, I want to have priority. They are right. No priority in 802.3. And then beyond that, they thought that Ethernet is like a sort of like ISM bands. Everybody hops in. There is no rules. There is no etiquette. But in a time division multiplex based, which is like token based, environment is more controlled. This was the, perhaps at that time was, I mean, people, before they do the industry, before they do it, they are paranoid about it. For example, when wireless started, everybody was paranoid about the health, one of the health. a lot. Later on, they find out that, yes, it may have. But still, they are continuing. It's a major industry. But the other thing that they were worried about it was interference, for example. A lot of 802.11, in fact, a standard committee time, was spent on the interference of what? Microwave oven. That was a major issue that they debated for like a... But when it came to implementation, really, in practice, it was just a paranoia at that time. In practice, it's not as important. Okay? There are other issues more important than that. So at that time, this is how everything works in telecommunication. You have an image before implementation, and you have an image after implementation, just like live. Very similar. Okay. These are images before implementation. And then based on that, they go and they implement. The next thing that they wanted was, okay, we have 802.5 now. Why shouldn't you use 802.5? 802.5 solves a lot of problems of 802.4, but they had in the early days this problem of breaking the cable. Because at the early days, they were not yet to this point that all the cables come to the central point. They had one ring. And they were saying that now if the ring gets broken, this is a controlled environment, it's very bad. So we have to go with the alternative of ring, which is really token bus, which is really a logical ring. Okay? Means a ring which cannot be broken physically. Okay? So more or less, this is how they started. But another issue that they wanted to do, which was very specific for 802.4, was that in 802.4, you wanted to have a more rugged environment, like cables, like 75 ohm cables, which are like TV cables. So, and you have different mediums. If they are available, you can work on that. For that reason, the physical layers that they picked up were completely different from the physical layers that they picked up for 802.3 and 802.5. So basically, the major difference between 802.3 and 802.5 and 802.4 is the physical layer. In 802.4, they are thinking about like carrier band, if you remember. Carrier band was the time that you have a cable, but only one user uses that cable, but does modulation. It's not baseband. Do you remember that? Then they were using broadband as well. What was the difference between broadband and carrier band? Broadband was like one cable for one user, or one connection. Broadband was one cable for several users. Means that it's like cable TV, several channels in one. That's broadband. Okay. Carrier band means that you have one channel over one cable TV. Okay. Apparently, carrier band is what? Less expensive. Okay. Because the modems that you design, they don't need to confine their bandwidth. In modem design, confining the bandwidth associates with cost. Okay. Now, if you want to have multiple channels, you have to have better filters and more confined signal processing environment. As a result, it's more expensive. So they come up with these options, which could be less expensive and more expensive options. Less expensive is carrier band, more expensive is broadband. And you leave those as a standard and leave the development community to develop that based on that. In addition to that, also, everybody has something for fiber optics. Okay? So they have something for fiber optics as well. Now, if you want to get like these four options, then this table that I have in here gives you an idea about a good summary of everything in 802.4. In this column and this column, you have like carrier band, two options. One of them is continuous phase. The other one is phase coherent. Phase coherent modulation is more difficult to be implemented. And this one is non-continuous phase, is easier to be implemented. So these are different costs associated to that. Now, in addition to that, the data rates that you can support with non-coherent phase and coherent phase are going to change. Okay. So basically, these are the options that you have, that they have specified in the standard. You have 1 megabit per second for carrier band, okay? 5 and 10 megabit per second for carrier band coherent, which is more complex receiver. Coherent means receiver and transmitter are synchronized. Non-coherent means receiver and transmitter are not synchronized in terms of the carrier. That addition involves additional cost and complexity to synchronize these two. It's synchronization of the carrier, not the bits. Okay. Then comes to broadband, which is multi-channel. They have 1, 5, and 10 megabit per second options. For fiber optics, they have defined 5, 10, and 20. Okay. For the fiber optics, the modulation techniques is Manchester coding on-off key. Okay, very similar to what we had earlier. Okay. But for these guys, modulation techniques are the ones that I have described in here. Do binary AM PSK modulation. This is amplitude and phase shift keying mixed. It's like a QAM. Do binary is the one that correlates 2 bits to one another. Okay? Do binary. Every 2 bits are correlated to one. These are complex modulation in a sense. Okay? Now, but when I come to the broadband, a standard specifies the bandwidth. Okay? 1.5, 6 megahertz, 12 megahertz for what? 10, 5, and 1. When I come to carrier band, they don't specify the bandwidth. Okay? The reason that they don't specify the bandwidth is that in carrier band, I have only one user. You go and design whatever you want to do. But if I have broadband and you design a modem, your bandwidth has to comply with these values. Because otherwise, your product doesn't work with the product of other people. Okay, so this is one additional thing. The other one is carrier frequency. When I have carrier band, since I have one user, I have to specify carrier frequency. But if I go for broadband, I don't need to specify that because there are multiple channels. Okay? So these are like 2 things that has happened in here. Other than that, these are the modulation technique that we talked about earlier. For optical, they have on-off. For broadband, they have amplitude and phase shift keying. Something similar to QAM. For carrier band, coherent, they have coherent FSK. For phase continuous carrier band, they have non-coherent FSK. Okay. Now, when you go to carrier band is very similar to baseband. It's omnidirectional. Means signal goes in 2 directions. Okay. When you go to broadband, it goes only in 1 direction. Okay. Then these are the transmission mediums. Transmission mediums for all of them are 75 ohm cables. Okay. And this is the fiber for itself. Then scrambling, they are not using scrambling for these places. For broadband, they use scrambling. Scrambling is like a technique that you use to scramble the data so that if you have strings of zeros or strings of ones, okay, still you have a lot of changes. Okay, that's called scrambling. Okay. And always for modems, for example, modems which are used on the radio or on the broadband, they have scrambling. For the baseband, they don't have scrambling. Okay. That's more or less what it is. We will see scrambling a couple of more times later on. And then I give you examples of how a scrambler works. Some examples later on. Now, so how does, now that was about the physical layer of the 802.4. Now, how does the medium access control works? Medium access control is really a logical ring. Means that each station has an address 10, 20, 30, 40, 50, 60, and they have a table which says who is next. Okay? So you can start with the 10 and go to 60. 60 comes to 50. 50 comes to 30. 30 comes to 10. How about 20 and 40? 20 and 40, they don't want to send data. They could be printers, only accept data. Okay? So they can be out of the ring. Okay? But these things are in here, the rings. Now, what will happen is that each station has like an address, and it needs to know the previous and the next address. So always you have to maintain that. Now, if somebody comes into the network or somebody is deleted from the network, you have to adjust these numbers. Okay? Then the next issue which comes in here, in 802.5, token was produced by what? Control, and maintained with the control station. In here, token has to be maintained distributedly. So everybody has to somehow maintain that. Okay. But anyways, the general structure is like this. I have a boss, but inside the boss, people are taking turn to go one after another. Okay? So it's like a time division multiplexing. But it's a random time division multiplexing, in a sense. Okay? Now, logically, it is ring. Physically, it's a bus. Okay. Now, what is the packet format? This was the packet format of 802.5. This is the packet format of 802.3, 802.4. 802.4, again, preamble it does have. Because it's more modem-oriented, more analog. Modems are analog devices. Okay, so they have preamble. Other than that, you have a start-up delimiter, and then you have frame control. Why do you need frame control? Because you have instructions for maintenance of the network. Then you have destination address, source address, the same addressing format of 802.5 and 802.3. They share the same thing. Then you have the data, and then you have error correction, exactly the same as before. And then you have end of delimiter. You don't have this frame status in here at the end. Okay? And you don't have this. Other than that, I mean, the general format in here is very similar. From here up to here is very, very similar to what? 802.3. The only difference is that in here the data is only one field. In there was 3 fields. And in here you have 1 byte for instructions. Okay? Other than that, this is exactly the same. Oh, and also you have end delimiter in here. Okay? So the packet formats of 802.3, 4, 5 are quite similar to one another. Okay? Now, frame control also has priority bits. Frame control can be used for 2 purposes. It can use for data frames, and it can use for control frames. If it is used for data frame, it carries the priority. Okay? Carries the priority bits. 3 priority bits. Means that I know I have data in here, and this guy which is in here, frame control, gives me what is the priority of data. Sometimes I don't have the data in here. I have only a control signal. If I have a control signal, these bits which are in here will tell me what type of control signal it is. Okay? So there is no priority involved in there. That's basically what it is. This is the priority scheme in here. You have a bunch of timers, and the timer is clicking, and you go over different priorities to see which priority you have, and at that priority level, you send if the timer is still alive. Okay. That's now control functions. Control functions that they have for 802.4. One is how to add a terminal to the ring, how to delete a terminal to the ring, how to initiate the ring, how to recover the token if token is not there. Okay. For these they have algorithms. Detail of these algorithms are implemented with these instruction sets, if you want to call. Okay. And these are the detail of the algorithms. This is the algorithm for addition to the ring, which basically what you have to do is you have to just adjust the table of the addresses, next addresses. So if I come in, I have to next one, change the previous address for the next one, change the next address for the one before. So you have to create a protocol for that. This is the protocol that they are using in there, which we don't go over the detail of that. Now, if you want to delete, you have to do reverse of that. This is the protocol that they do for that. Okay. And if you want to initiate the ring, initiation of the ring, then again you need another algorithm. These algorithms similar to that for Bluetooth, for initiation of the network. Okay. Now, initiation of the network means that you come to the network. You want to see that if there is anybody else in there. So first you have to scream that if there is somebody else in there, or you have to passively sit down and listen. In here, passively they sit down and they listen for a period, then they scream. And then they see that if somebody answers to that scream. If somebody is answering to that scream, then they can negotiate that what is going on after that. Okay. But detail for not needed for this course because it's obsolete. Then the last operation that they have is just the token recovery. Token recovery means that token is lost. Who wants to recover that? They have an algorithm for that too. That's more or less what it is. So in summary, if you want to compare the token bus with 802.3, 802.3 has a simpler algorithm, is all over the place. It has a fair access, good performance at the low and medium loads. These are the same things that it had over what token ring. And then disadvantages of 802.3 is collision detection is analog, and fault diagnostic cannot be done. Minimum packet size is short for some of the applications. Poor performance under heavy load, and it's biased to long transmissions. For token ring, the advantages are it's very similar again to the other one, to the 802.5. The throughput at high load is good. Tolerance to the range of data packets, and access is controlled. That's the main paranoia is access is not controlled, and access is controlled in here. This is the best access control. But the difference between that best and least doesn't make any difference for the user today. Okay. And the bad part of it is that it's complex algorithm, and it's an unproven technology. Means that not many people use it. And this is one way. These are the comparisons that Stalling was making in his previous book between 802.4 and 802.3. And this was my last slide, I believe, for this lecture 7. In summary, what we did, we went one lecture. This was 2 parts. The first part was 802.3, which is the simplest actually. The second part was a quick overview of 802.5 and 802.4. And I think the things that we can carry from here on, one is like this coordination of the terminal problems and algorithms associated to that. The other one is packet format structure. Then is issues related to the physical medium. So far, for the physical medium, everything has been very simple, relatively simple. When you go to fast Ethernet and gigabit Ethernet, gradually you have more complex transmission mediums. MAC is not important anymore as much. Okay. The same is when you go for what? For wireless. When you go for wireless, you need new MACs and much more complex physical layers. Okay. And these are the material that part of that we will cover in the following 2 lectures. for the wired networks and one lecture on the wireless at the end. And in between we will have 2 lectures on wide area networks, hopefully on the bridges and routers, and one on hopefully on the wireless wide area networks. I have to see how much time I have. Okay? So I'll see you this Thursday for the exam.